Mr. Benson here with rearranging equations, which is the next idea we need to look at. Now this is very similar to what you've been looking at already in terms of the skills, but the end result is slightly different. So we've been looking at solving equations. So for example, to find x if 3x minus 3 equals 15. Now you can see in an equation like this one here, there's only one quantity that we don't know, which is the x, and so you know that you can solve that. Now the way you do it is you work through a process of doing the opposite operations to each side until you end up with x by itself. Now rearranging, or also called transposing, is when we've got an equation like this in one form and we want to change it into a different form. Now often there is more than one thing that we don't know, so we're not going to get a numerical solution, but we're going to get a different form of the equation that we might be able to use in other ways. The steps that you follow are exactly the same. So here's an equation and we want to rearrange it to make x the subject. Now the subject of an equation is the pronumeral by itself on the left hand side of the equal sign. So at the moment y is the subject, but we want to make x the subject. So what we do is the same sort of things that we've been doing when we're solving equations. We look at what's happening to x and we do the opposite things. Now because of our order of operations, with this example, the first thing we would do is we would subtract x from both sides of our equation. These would cancel and we would end up with y minus 6 equals 2x. Then to get x by itself, the last thing we would do is we would divide everything by 2. Make sure that you are dividing everything by 2 on both sides of the equation. These would cancel, and so what we're left with is x equals y minus 6 over 2. Now you could simplify that somewhat, so you could say that's the same as y over 2 minus 3, or we could also write it as that's the same as a half y minus 3. In some ways this last way is probably the preferable way of doing it, because it's a form of equations, or it's the standard form of linear equations that we'll talk about a lot later. But as you can see, I haven't done anything different to all the examples we've done before. I merely identify an operation and then I do the opposite operation to both sides so that my equation stays balanced. Some examples. So this first one here is the relationship between temperature in degrees Fahrenheit and degrees Celsius. Now if you've ever done any cooking, you might have come across some recipes that talk about Fahrenheit. And we need to do that conversion. So let's rearrange this to make C the subject. So again, I'm going to do the opposite thing to both sides. Now the first operation I'll be dealing with is subtracting 32 from both sides. These will cancel, so what I'm left with is f minus 32 equals 9 over 5c. Now there are two ways I can approach this. One of them is that I can think about this as being one number, one fraction, and so I can divide the left-hand side of my equation by the one fraction. Alternately, and this is possibly simpler, I can do it in two steps. So I've got a multiplication and a division. Now I'll get rid of my division first, so I'm going to multiply this by 5 on the right hand side, and I'll also do that on the left hand side, making sure that I'm multiplying everything by 5. So the 5's cancel on the right hand side of the equation. So what I'm left with, and I'm just going to swap these over, is 9c equals 5f minus 32. Now then to get rid of the 9 on this side, now I haven't expanded this, you could, it's the same thing, it doesn't really matter too much. At the moment I just want to get rid of the 9. So I'm going to divide everything by 9, which will cancel those, divide everything by 9 over here. Now I could express this perfectly well as 5 over 9 f minus 32 is probably the easiest way of doing this equation if you actually wanted to convert from one to another, because you just do the subtraction and then the multiplication. We could expand this out. Now it's going to be a little bit trickier because of the fractions and the fact that there are not a lot of common factors in all these numbers. I'm going to leave it as it is at the moment because you can see that we've managed to make C the subject, although this perhaps could be simpler. If you go into subjects like physics, there are a lot of formulae, physics, chemistry, any of the sciences really, you'll use a lot of formulae in different ways. So here's a formula that describes acceleration. So acceleration of an object is its final velocity minus its initial velocity over the time taken. Now, if we want to rearrange this equation to make the initial velocity the subject of the equation, which is a pretty common thing to do, again, we just follow the same steps. Now, because we've got this common denominator of t on this side of the equation, I've mentioned before that the easiest thing to do is just to multiply that to get rid of it. So I'm going to multiply by t on the right-hand side. I'm going to multiply by t on the left-hand side. So a times t is, we're just going to write that as at. On the right hand side, the t's will cancel, so we've got at equals v minus u. Then to get u by itself, I would want to subtract v from both sides. My v's will cancel, so then I've got at minus v equals minus u. Now, I remember that I've said before that if I've got a minus x or a minus u or something like that, if I want to make it positive, I just need to change the signs of everything. So minus u becomes u, at will become minus at, v will become positive v, so it will be v minus at. Now, we can also use this to use more complex and nonlinear equations. I particularly want to show this because some of you will get onto nonlinear equations like quadratics, and some of you have already looked at how logarithms are the opposite of exponential or indices equations. So what we can do with an example like this, now this is again from physics, where we have the kinetic energy of a moving object is a half of the mass times the velocity squared. Now if we want to make v the subject, which is also a really common thing we do in physics, we've just got to think about the things that are happening to v. Now v is to the power of 2. Now if you think about your order of operations, BODMAS, brackets are first, order, which means powers or indices, is second. So because we are working backwards, we'll actually worry about that last. So everything else we're going to do is going to happen first. So another way you could think about expressing this one is that it's the same as E times mv squared over 2. We're effectively dividing by 2 here. So the first thing that I'm going to do is I'm going to multiply both sides of my equation by 2 to cancel that out. So we'll cancel the 2's on that side, so we've got 2e equals mv squared. So far there's nothing here that's any different to what you would have done before with linear equations. Then to get the v squared by itself, I'm going to divide both sides by m, cancelling my m's on the right hand side. So now I've got v squared equals 2e over m. Now the only thing that's slightly different here is we've got to think about the opposite operations. Now the opposite of squaring something is to square root it. So we'll take the square root of both sides. So the square root of v squared will equal the square root of 2e over m. Now the square root of v squared is just v. So the square and the square root cancel each other. So we get v equals 2e over m. Now if we go on to a compound interest equation, now again this is involving indices. What I'm actually going to do in this equation is I'm going to find n. I'm going to make n the subject. Now what can we do with this one? Well, at the moment I can't expand my brackets because it is p multiplied by 1 plus I all to the power of n. So I can't do anything with this term at the moment, but I'm going to get, so I'll see what simplification I can do first before I worry about this bracket and the power here. So I can divide both sides by p. That seems like a simple thing to do, and again it's the sort of thing we've been doing already. So I get 1 plus I, whoops, 1 plus I, not exclamation mark, to the power of n equals a over p. Then what I've got to think about here is what is the opposite of doing to the power of n, and the opposite of that is actually doing the log. So in a situation like this where you've got something to the power of something that we don't know and we want to find, we're going to use logs to make our equation into a form that we can use. So we're going to take the log of both sides. Now if you haven't looked at my log videos, then this probably is not going to make a huge amount of sense, because you need to be thinking about your log laws when we're doing something like this. Now the log laws are basically the same as our index laws. So what we've got then is that the log of something to the power of something else is equal to the power times log of the base, if you like. So we got n log 1 plus I equals, now with the log laws for division are a lot like the index laws for division, where we know that we subtract the indices, so we're going to subtract the log, so it's going to be log A minus log P. And so now to get this by itself, what I've got is I've got n times log 1 plus I. Now I can't figure this out at the moment because I don't know any of these quantities, but I can rearrange this to get n by itself, because what's happening here is multiplication. So the opposite would be to divide both sides by log of 1 plus I, which I'll do. So over here they cancel and I'm left with n equals log of A minus log of P over log 1 plus I. Now look, this is quite an advanced example in comparison to the simple linear ones I've been showing you before, but the reason I really want to emphasize it to you is that you can see that just by following the process that we've been looking at, identifying operations in the correct order and doing the opposite operations to both sides, we can solve or rearrange quite advanced equations.